So some guy comes up to you in a dark alley and he says, "Hey kid, you want $1?" And you say, "Sure." And he says, "Well, get me the current going through every one of these resistors." And so he draws the following circuit diagram for you. There's a resistor there, and then there's this funky point right here. It doesn't look so funky yet, but he's just dropping resistors all over the place, and you know it's going to be a long evening, but you've only got 15 minutes to solve the AP problem. So you'd better get working. I mean, the problem posed by the strange guy on the street, who's going to give you $1 if you get it right. We got resistors all over the place. So this is our first picture of this circuit diagram, and he starts giving you some numbers. Turns out he's a pretty nice guy. You talk about his kids, everything's fine. There's a 12-volt battery powering this circuit, and he wants to know what current, and I'm going to choose myself a color here. He wants current through each thing and voltage across each resistor. So that's the language that we use. The current goes through a resistor and the voltage is across a resistor. Voltmeters would come on here like this. I'll just draw you a voltmeter. Here's the voltmeter that comes on here, and you would connect like that. Because see, a voltmeter, an ideal voltmeter, has infinite resistance and no current. Given the choice, the current's coming out here. The current's like, oh, I see infinite resistance or some finite resistance. It chooses to go through the resistor. An ammeter is the opposite sort of thing. An ammeter right here would actually, an ammeter would be in line with, there we go, it's an anarchy meter. No, just kidding, it's an ammeter and the current's going through the ammeter. Now ideally the ammeter has no resistance at all. So I should draw this ammeter green to try to stay with my program there. But the ammeter will log the resistance through this nastily drawn resistor. Let's see if I can clean up this resistor a little bit. And it would give us the current going through that resistor there. So here's the procedure. Let's make this thing a real problem by giving you all kinds of resistor values. This one, he says, is 68 ohms, and this one, he says, is 5 ohms. He wants this one to be 12 ohms. I don't know where he's getting these, because these are not standard resistances, but somehow he managed to get all of these. 30 ohms. Set up this problem yourself so that you can also do this, and pause me whenever I get ahead of you. But I'm going to use equivalent resistances to find the overall resistance. This is my battle plan. I'm going to find the overall resistance of the circuit, and then I'm going to say, hey, if I've got a voltage and I've got some resistance over here, how much current will be going through the circuit as a whole? And then I'll notice that that current is present here, and it goes through this resistor. So the overall current will go through this one, and it will come back and go through that one and get back into the battery. But you see the current forks right here. It's got 3 different paths that it can take. So this is going to be a little bit complicated, but my intention is to solve the entire problem with V is IR and equivalent resistances in parallel and in series. So this is series equivalent resistance is R1 plus R2 plus R3, etc. And for parallel, I know that 1 over the equivalent resistance is the sum of the inverses of the individual resistances. And we will play with those so that you get a feel for how this pattern works. Okay, my plan is to use these 3 simple relationships to solve the entire problem. And to do it, I'm going to keep track of which sheets I'm working on, and I'm going to ultimately come back to this sheet and fill in every bit of information, V, I, and R, for each resistor, given the resistances already. So I want to simplify this messy thing right here, and I'm planning to draw it just a little bit differently. I want to draw myself a battery and a resistor right here, and then you see I've got these 3 paths. See my 3 paths that I have right here? So I'm going to take one down right here and then bring it back. Well, shoot, there's a resistor right here. Sorry, this is a little bit sloppy. I'm going to try to do a little bit better next time. Now, this intersection here, it's got 3 of them, so I'm going to draw one coming out here and then down that way, and the third one is going to be over here, and that way, and then that way, and then back. Do you see how that is the same map as what we've already done? So now I label these guys. This is picture 2, by the way, but we've got 68 ohms, and 5 ohms, and 30 ohms, and 5 ohms, and this sucker is 12 ohms, and that sucker there is 12 volts. Now, I first need to recognize, before I actually simplify it, that was just cleaning it up, I first need to recognize what is the combination of resistors that I can analyze first. It looks like these 3 resistors are in series, but they're not because there's something in parallel with it. It looks like these 2 resistors are in parallel, but they're not because there's something else in parallel with them. In addition, it looks like these 3 are in parallel with each other, but it's not that simple because these two are in series with them. So I'm looking for the absolute simplest combination of resistors that I can find, and I think it's these 2 5s together. So if I use the equivalent resistance formula for series resistors, I'm just going to find that the equivalent resistance is 5 plus 5. So that's 10 ohms. And I love finding series resistors because I can simply add them. So as I go to the next slide, I want to point out that this will be 3. And my system now looks like this. I've got myself a 10 ohm equivalent resistance here. And here I've got 30 ohms still, and here I've got 5 ohms still. And then over here I've got 68, and the battery is there, and over here I've got, what did I say, 12 ohms here, and 68 ohms there, and 12 volts. Okay, so there's slide 3. In slide 3, I now see very clearly that these 3 are in fact in parallel, and I try to find the equivalent resistance for those guys right there. Let me point to those. Well, let's see, I'll put it down here. Our equivalent is 1 over the sum of all those. 1 over 5 plus 1 over 30 plus 1 over 10. Wow, adding more down here actually makes my answer, makes my answer, what, bigger or smaller? Well, you'll have to figure that out. Play with that and make some sense of it. But right now, I'm going to do that calculation so I can get myself the resistance. Boy, I hope I don't make a mistake. That would be dreadful. I got 3 ohms. So check this out. This resistance of the 3 of these guys, if they are acting as a single resistor, is less than all of the individual resistances. I think that's cool, and I think we should move to slide 4 at this point. Slide 4 has still, as I simplify this further, it's still got a 12-volt battery. And we come over here to a 68 ohm resistor. And then there's this other resistor here. We just found this to be only 3 ohms. And then it comes in here, our circuit continues over here, with the 12 ohm resistor. Now, this equivalent, this equivalent resistance is 3 ohms. And so now we don't have to write the 5 and the 30 and the 10. That's sort of like if you find, if you've got a vector this direction and a vector this direction, instead of using these 2, which might be the components of an overall vector, you're going to use only the overall vector itself, the vector. So instead of using the individual resistances, we're using just the overall resistance. Now we see that these 3 are simply in series. So then I say the equivalent resistance here is, well, it's just 68 plus 3 plus 12. I'm going to get my calculator. Just kidding. I think I get 83. All right, then the final diagram looks like this, and then we'll work our way back up, filling in all the information that we need. The final diagram looks like this. There is a 12-volt battery, and the 12-volt battery is sending current through an 83 ohm resistor. And now I've got to use these 2 colors to fill in the voltage across the resistor and the current through the resistor. So it's a very simple circuit, and I say V is IR. And so, well, I like to go around this circuit and define some voltages. That's 0, and it's equipotential for this, so that's also 0. And this is 12, and it's equipotential for this, so that's also 12 volts. And what did I say I would use for voltage? I think I wanted to use blue for voltage. If I'm trying to find the voltage, well, the voltage will be 12 volts. Cool. And what about the current? The current through this resistor, I total, that's the total current through the circuit. The current through that resistor, well, I guess it will be V divided by R. So I got my 12, I'm going to divide that sucker by 83, and I find that the total current is going to be a small number. In fact, we'll be working with very, very small numbers. 0.1458 amps. All right, that's a reasonable amount of current for a circuit. We don't want hundreds of amps or anything like that. Now, I'm planning to take this current here and see where it goes on this circuit. See this circuit right here? Where's that current gonna go? What can I do here? Clear out some of this nonsense. That current that goes through this equivalent resistance will be going through this resistor and that resistor and that resistor. So I can write that green down all over the place. I can call it here. I've got my I. Now, you remember there's no backing up of current. So following the principle of diarrhea, this will be exactly the same as all these others. 0.14458. 14458 amps. I is 0.14458. In fact, there's something pretty interesting going on here. We again say here I is 0.14458. As soon as I get back to a resistor that actually exists in my diagram 1, I can actually fill in all the information from that resistor. So this 68 ohm resistor is the 68 ohm resistor from diagram 1. And the 12 ohm resistor down here is the 12 ohm resistor down there. This 3 ohm resistor is a combination of all 4 of those resistors, so we can't work with those yet. But I do know the current here, and if I know the current, then I can know the voltage drop because V is IR. So we'll put that down right here and point out how I'm going to get V for this. So this is 12 volts here, and then there's a voltage drop across that resistor, and that voltage drop has to be the current going through the resistor, which we said is this amount, going through the whole circuit, times that resistance. So I've got that number right there in my calculator, and I'm going to multiply it by 68, and I find that the voltage drop across this resistor is 9.8313 volts. What does that mean this voltage is right here? Well, it doesn't mean it's 9.8 blah, 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 blah. It means it's 12 minus all that business right there. So I'm going to take 12 and subtract my answer, and I find that this voltage is, this voltage is 2.169 volts. We might have some rounding things as we continue on. But, well, what do you think the voltage is over here? We're going to have a voltage drop, and it's going to be equal, the voltage drop across this resistor is equal to the voltage of this resistor times the current that's going through it. Oh, you see how everything's going to work out here? Let's try that again. I'm going to go back up and get my 0.14458, and I'm going to multiply it by 3, and I find that the voltage drop here, the voltage drop is 0.43374 volts, which means if I take 2.169 and I drop the voltage going through here, that's what the current does. The voltage decreases because the potential of the charges that are moving through here, pretend it's positive charges, right? Well, the potential of the charges is going to be decreasing. So I take 2.16867 whatever, blah, 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 and then I subtract I subtract that answer, which was 0.3374, and I find the voltage at this location right here. This voltage is going to be 1.7349 volts. Now I want to know the voltage drop from here to here, and by gum, I hope it's 1.7349 volts, because this has to be 0 if that's 12, because batteries cause a voltage rise, not a voltage drop. So let's see what we get. I'm going to take this resistance and multiply it by this current and see what it is. I got 12 times 0.14458. Enter equals, it is. That is the voltage across this resistor. We find that to be 1.735 volts. And so this, if I take 1.735 volts and I subtract 1.735 volts, I find that that is 0. And that's a happy thing for a battery. It starts at 0, pumps up to some voltage, and that's the reason that the charges move. The battery is giving the charges energy, and the charges move through the circuit as a result. I'm not going to be in so much detail when I go to step 3 because, see, I can immediately fill in, as we were saying, I can immediately fill in the voltage and the current through this resistor because it's the same resistor. And I can do the same thing for this 12 ohm right here. I've got all that information. So I know that the voltage here is 9.8313. That's the voltage drop across that resistor. And I know the voltage drop across this resistor down here. This voltage is 1.735 volts. And I also know the current through each of these resistors. This current is, I'm on number 1, so this is my final answer. I'm already filling some information in on that, and I'm about to get my dollar. 4458 amps. And this guy right here is also experiencing the same current because all the current's going through here. There hasn't been any forking yet at this resistor. Over here, all the currents have come back together and I'm going to get the same current that's going through the battery, and it's the total current of the circuit as well. So that's 0.14458 amps. Now, we'll come back to situation 1 in a little bit, but we now have to figure out what's going on because there's a voltage drop across this resistor, but it's an equivalent resistor. And there's a current going through this resistor, but it's equivalent resistor. In fact, it was equivalent to these things, a 5, a 30, and a 10. So what do we know then for each of these 5, 30, and 10? Do we know that they each have this current, or do we know that they each have this voltage drop? And the answer to that question is contained in these wires. These wires are equipotentials, which means that if there is a potential here, then it's the same here and here. And if there's a potential here, then it's the same here and here, because they're all the same potential. So I can do this in a number of ways. I can start by my battery. I like to do that. Let's start from my battery. I'll say that this is 0, and this is 12 volts. This location right here is 0, and the location there is 12 volts. And that means that this location, we still got that same voltage drop here. So this location up here is 2.169 volts. And the location down here on the other side of that equivalent resistance, well, it's all of this area here, but that's 1.7349 volts. So the voltage drop across here is the same for all of them. And I simply have to subtract those two guys, or I could look over here because I wrote it down at 0.43374. And I'm going to write that down sideways. V equals 0.43374 volts. 43374. Okay. V equals 0.43374 volts. That's the voltage drop across each one of these resistors. And now my plan is to figure out how the current is. You want to guess which one of these resistors has more current? How about I ask you to guess that right there? Which one of these resistors will have more current? If they all have the same push on them, I suppose the one that's easiest to go through will have the most current. The one that's easiest to go through is this one. So we predict this will have the most current. In order to find current, I'm going to say current is V over R. R is in the denominator. Of course, the one with smaller resistance will have a greater current, and let's figure it out. I'm planning to take this voltage and divide it by that resistance. So here we go. I got 0.43374, and I'm dividing it by 5, and it's an even smaller current. The current through this guy right here, 0.0867 amps. That's the current here. And the current through this guy is, well, it's that same voltage but divided by 10. So I guess it's going to be half as much current as right there. And that's true. It's 0.04337 amps. And oh shoot. No, that's my 10. Sorry, that's my 10 over here. It should be through this resistor, 0.0433374 amps. But problem is, this was an equivalent resistor, so we'll have to get back to that on the next slide. And the final thing that we need to do is divide the whole thing by 30, and we'll find that there's even still less current going through this really, really resistive thing. That's just 0.014458 amps right there. So all of these currents together, though, they will add up to the current that we had in the previous slide. the current that we had in slide 4 was 0.14458. And if you're feeling spunky, I would suggest that you add this and that together. I hope that you will get that answer right there. That would be awesome, right? Because what we're seeing is the current that's coming in here is forking in 3 different paths, and it's not forking evenly. It prefers most of the current, well, the plurality of the current anyway. Most of the current? Yeah, in fact, even most of the current is going to be going through here, and a tiny bit going through there because there's a lot of resistance, but still a little bit going through here. So as I present more and more paths, even if they're very high resistance, a tiny bit of current will go through them, and it will enable the total current of the circuit to get larger. That's why additional parallel paths decreases resistance. Because it increases current. I mean, that's one way of looking at it anyway. Do we have this all figured out? We were going to copy some more numbers on here. No, I think we've got everything that we need to go to slide 2. In slide 2, really slide 2 is our final slide because slide 1 was just a slight tweak on this sucker. I'm going to take that information and write it down here, but I don't need to. I mean, we've already figured out this 5 completely. Check. We've already figured out the 30 completely. Check. We've figured out this 68 completely. Check. And we figured out that 12 completely. Check. Now, our final conclusion has to be what's going on with these 2 5s. Remember, we created a 10 out of the 2 5s because of the principle that adding up 2 resistances in series will give you the equivalent resistance. I know the voltage at this location is oh shoot, I'm supposed to use blue. I'm so sorry. The voltage at this location is 2.169 volts, and the voltage at this location is 1.7349 volts. So that means, well, I mean, I guess I could ask you what the voltage is right there. What do you think? These are equal resistances, so you're kind of guessing it might be the average of those two. You'd be right if you do that, but how can we do this more carefully? I'll tell you. We know the current that's going through this resistor and the current going through that resistor. In fact, it's the same as the current that's going through the equivalent resistance. Notice, you have to be really careful. You have to know whether I'm saying the current is the same or the voltage is the same. I guess if it's parallel, the voltage is the same, and if it's series, the current is the same. So you'll really start to get a feel for that as you do a few of these problems. You have to do them to know what the heck's going on, though. The current through this guy, 0.0433374 amps. And the current through this guy, 0.0433374 amps. Sure. Now, what is the voltage drop across this resistor? Well, it's going to be the current times the resistance, because V is IR. So I'm going to take 0.043374 and multiply it by 5. And I find that voltage drop. The voltage drop across this resistor is 0.21687 volts. That means, I'm going to do the same math to get this other one, and I find the voltage drop from there to there to also be 0.21687 volts. Sure, which means that that is the average of the two of them, and I guess if I multiply that by 2, if I multiply this number by 2, I get the voltage drop from here to here, and so if I take that number and add it to 1.73, I'm adding it now to this number down here, 1.7349 volts, I find it to be, this number up here, 2.169 volts. Okay, cool. So that's the voltage across each of these resistors, and the current through each of these resistors is the same as the current going through there. And if we wanted voltage and current across every one of the resistors in our original problem, we have in fact done it. And presenting it in a neat way is not really possible because there's an enormous amount of information and several decimal points because I chose these resistor values at random. But that's how it's done. By a circuit, and he wants to know what current, and I'm going to choose myself a color here. He wants current through each thing and voltage across each resistor. So that's the language that we use. The current goes through a resistor and the voltage is across a resistor. Voltmeters would come on here like this. I'll just draw you a voltmeter. Here's the voltmeter that comes on here, and you would connect like that. Because see, a voltmeter, an ideal voltmeter, has infinite resistance and no current. Given the choice, the current's coming out here, the current's like, oh, I see infinite resistance or some finite resistance. Chooses to go through the resistor. An ammeter is the opposite sort of thing. An ammeter right here would actually, an ammeter would be equivalent resistance is R1 plus R2 plus R3, etc. And for parallel, I know that 1 over the equivalent resistance is the sum of the inverses of the individual resistances. And we will play with those so that you get a feel for how this pattern works. Okay, my plan is to use these 3 simple relationships to solve the entire problem. And to do it, I'm going to keep track of which sheets I'm working on, and I'm going to ultimately come back to this sheet and fill in every bit of information, V, I, and R, for each resistor, given the resistances already. So, I want to simplify this messy thing right here, and I'm planning to draw it just a little bit differently. I want to draw myself a battery and a resistor right here in line with, there we go, it's an anarchy meter. No, just kidding, it's an ammeter, and the current's going through the ammeter. Now ideally the ammeter has no resistance at all. So I should draw this ammeter green to try to stay with my program there. But the ammeter will log the resistance through this nastily drawn resistor. Let's see if I can clean up this resistor a little bit. And it would give us the current going through that resistor there. So here's the procedure. Let's make this thing a real problem by giving you all kinds of resistor values. This one, he says, is 68 ohms, and this one, he says, is 5 ohms. He wants this one to be 12 ohms. I don't know where he's getting these, because these are not standard resistances. So some guy comes up to you in a dark alley and he says, "Hey kid, you want $1?" And you say, "Sure." And he says, "Well, get me the current going through every one of these resistors." And so he draws the following circuit diagram for you. There's a resistor there, and then there's this funky point right here. It doesn't look so funky yet, but he's just dropping resistors all over the place, and you know it's going to be a long evening, but you've only got 15 minutes to solve the AP problem, so you'd better get working. I mean, the problem posed by the strange guy on the street, who's going to give you $1 if you get it right. We got resistors all over the place. So this is our first picture of this circuit diagram, and he starts giving you some numbers. Turns out he's a pretty nice guy. You talk about his kids, everything's fine. There's a 12-volt battery powering this, but somehow he managed to get all of these. 30 ohms. Set up this problem yourself so that you can also do this, and pause me whenever I get ahead of you. But I'm going to use equivalent resistances to find the overall resistance. This is my battle plan. I'm going to find the overall resistance of the circuit, and then I'm going to say, hey, if I've got a voltage and I've got some resistance over here, how much current will be going through the circuit as a whole? And then I'll notice that that current is present here, and it goes through this resistor. So the overall current will go through this one, and it will come back and go through that one and get back into the battery. But you see the current forks right here. It's got 3 different paths that it can take. So this is going to be a little bit complicated, but my intention is to solve the entire problem with V is IR and equivalent resistances in parallel and in series. So this is series.